Hi, class. In this module, we're going to discuss hypothesis testing. This is really where we get into the heart of statistics, what most people think about when you talk about statistics is hypothesis testing. In this module, we're going to talk about the concept of hypothesis testing. We're going to actually save performing hypothesis tests till our next module. Some of these topics can be pretty complex, but I've supplied you with several different readings for this week. A lot of the readings are repetitive. You can see here on Canvas. But I wanted to kind of err on the side of giving you too much information. So if you don't understand one of the chapters or one of the readings, there's additional readings maybe help you understand that. If you look at the assigned readings for this week, we have the Kranzler text for chapter 10 in it. I have a couple note sections where I try to summarize some of the readings. Here's an introduction to hypothesis testing, some additional notes on confidence intervals. And then I have a lot of different optional readings. There's a good article from Practical Assessment, Research, and Evaluation on the concept of significance testing. There's a good article on here on, talks a little bit more about the standard error of the mean, which we'll talk about in a little bit. This was just a recent, from February 2016, from the Harvard Business Review. It was a refresher on statistical significance. There's also, a couple websites here that talk about hypothesis testing, and then just a few more links. So I think I provided you with a lot of resources on hypothesis testing. Like I said, a lot of the information is repetitive, but I wanted to make sure that you have plenty of support for this module. Because like I said, some of these concepts can be sort of difficult to grasp in the first read through. The assignment for this week is a quiz on hypothesis testing, and then we'll have a little discussion topic. It's mainly just a check-in. I just want to check in to see how everything's going with everybody. If anything's clear or not clear about what we're learning, if there's anything I can do to improve your learning in the class, I'd like you just to post it there so I can try to make this a good learning experience for you all. So this week, or this module, we're discussing hypothesis testing. Previously we've discussed ways to summarize and describe data. That's with what descriptive statistics are. However, researchers often want to know, often need other techniques to really formulate and test hypotheses. We want to know about the effectiveness of an experiment or how effective is our intervention. We also want to be able to generalize our findings from our sample to a larger population. Oftentimes we don't have the resources to sample or interview everyone in the population. So we turn to what are called inferential statistics. And in inferential statistics, we're really testing hypotheses about population parameters and making estimates about population parameters. If we had information on everyone in the population, we wouldn't need inferential statistics because, like I said, we had everyone in the population. A couple of concepts to keep in mind is, statistics are built on really the laws of probability. Statistical inference is based on probabilities. I'm not going to go into a lot of detail about probability. You can read more about it if you like, but basically probability is just a likeliness that an event will occur. You think about if you flip a coin, right? There's a 50-50 chance that the coin will land on heads. Probabilities range from 0, means there's no success, to 1, where it's a certainty of of success. But a couple of ideas to keep in mind is one, this idea of a conditional probability. And this is the probability that an event will occur given that another one has occurred. So you can think about this like, what's the probability of drawing an ace out of a deck given that I've already drawn an ace? So that'd be an example of what a conditional probability is. And we'll use this idea of conditional probability later on in this class and in other statistics courses. There's also the idea of independent events. You know, two events are said to be independent when the probability that one event occurs in no way affects the probability that another event is going to occur. And so these ideas are going to come into play a little later on. Here I have a little example of how you might encounter conditional probability in independent events. Just some terminology of population versus a sample. A population is that large group that we're interested in, and our sample is a subset of that population. If we want to make inferences back to the larger population, we want our sample to be representative of that population. There's an example here. You know, Cranston in the text talks about, you know, a hypothesis is, you know, a good hypothesis is one that's able to be rejected. You know, if you think about these two statements, there are squirrels in the park and there aren't squirrels in the park. You know, they're kind of getting at the same idea, but one's you're able to refute and the other one's not. If you take the first option, there are squirrels in the park, you know, what could you do? You could go to the park, you could look and look and look, but you don't see any squirrels. You know, of course, that doesn't mean that there aren't any there. You know, they just could be hiding. You know, all you can say is, you know, I went to the park and I didn't see any squirrels. But the second option is different. You know, you can reject the second option as soon as you actually see a squirrel. So the first one is actually hard to reject, right? You know, it's the whole idea of the absence of evidence. It's not the evidence of absence. And so Cranston talks about this in the textbook as well, about, you know, statistics do a good job of proving that something is false, but it's a lot harder actually proving that a hypothesis is actually true. All right, so hypothesis testing involves making inferences about a population based on observing a sample. You know, as Cranston states, you know, it's really difficult to demonstrate that a particular hypothesis is true. It's a lot easier to demonstrate that the hypothesis is false, like we did with our squirrel example earlier. So this is where the idea of a null hypothesis comes. You know, null hypothesis is a statement about a population parameter, and it's usually a statement that there's no difference. You know, since we usually want to demonstrate that there is a difference, say like there's a difference in between teaching method A and teaching method B, what we do is we hypothesize that the groups are really the same, and then if we can reject that hypothesis, we can say that the groups are in fact different. This is similar to the concept of proof by contradiction in mathematics. So say we want to compare teaching method A with teaching method B, two teaching methods on some form of math achievement. You know, the null hypothesis would be that in the population, the mathematic achievement is the same for those who learn with teaching method B and teaching method A. If we can then reject this hypothesis, then all we're left with is the conclusion that teaching method A and B are different, or that the mathematical achievement between those who are taught with teaching method A and teaching method B are different. In all types of tests, you know, when we perform a hypothesis test, we either make the correct decision or a wrong decision, right? You know, because of sampling variability, you know, all statistical tests have some type of uncertainty in them. And so there are really like two kinds of errors we can make. You know, we can either make a correct decision or we'd make either what's called a type 1 or type 2 error. So let's say that the null hypothesis is true and we don't reject it. Then we've made the correct decision, right? Well, let's say the null hypothesis is true. There is no difference between the two teaching methods, but we reject that hypothesis. That's what we call a type 1 error, is when we reject a null hypothesis and the null hypothesis is actually true. If the null hypothesis is false and we reject it, then we made the right decision again, right? That's the correct decision. That's what I'm showing here. If the null hypothesis is false, but we do not reject it, then we've made what's called a type 2 error. So in our statistical test, we have to decide how much error we're willing to take on. And so our statistical test, you'll see an alpha level. The alpha level is, what probability of making a type 1 error are we willing to accept? So if we set our alpha level at 0.05, then we're saying that we're willing to accept a 5% chance of making a type 1 error, or we're willing to accept a 5% chance of rejecting a true null hypothesis. Another way I like to think of type 1 and type 2 errors is I always like to pull up this little picture. So you see this doctor here in the picture on the left. He's telling this man that he's pregnant. Well, obviously, that's an error. You can also think of type 1 error as a false positive here. So we are rejecting the null hypothesis that he is not pregnant and saying that he is. A false negative is also what we might call a type 2 error. We're telling this woman here who's obviously pregnant that she's not. So some people think it's easier to think of type 1 and type 2 errors as false positive and false negatives. And if you can keep this mental picture in your head, it's a good way to help you think about these different types of errors. One point I do disagree with the Kranzler test is his argument that type 1 errors are more important. I would argue it really depends on the situation. Let's take medical testing as an example. So you might have a screening for a certain disease. Let's say the screening comes back positive, saying you do have cancer, whatever the disease is. If you do have cancer, then that's the correct decision. But if you don't have cancer, that'd be a type 1 error, right? It'd be a false positive. So let's say the test came back negative, but you do have cancer. That'd be an example of a false negative or a type 2 error. In this situation, I'd argue that the type 2 error is actually more important to control. So if the test comes back saying you have cancer, but you actually don't, you would go back, get some more testing, and eventually find out that you don't have cancer. But with the type 2 error, the testing comes back saying you don't have cancer, but you actually do. You go about your life thinking you don't have it, and you don't go back in for more treatment. So the whole point here is that I think which error is more important really depends on the situation. And finally in here, I have a little discussion here of the term statistical significance. When we reject a null hypothesis, when we say that the null hypothesis is not correct, that's we say that this effect is statistically significant. And we'll talk about this more when we talk about hypothesis. I want to just introduce you to the concept here. And then I also have a little bit of terminology here that's going to come up later for us to know. And you can read through my notes here, find out a little bit more information about all this. And I think the Kranzler test does a good job of introducing these concepts as well.